Right, so next we come on to the actual test results. So this is where we go to the consumer unit, and circuit by circuit, we will first of all need to identify, if we haven't got the information to hand, what is on each circuit. So in the case of lights, one of the circuits might be labelled upstairs lights, one might be labelled downstairs lights, but we need to confirm that, say for example as outside lights, we need to ascertain whether they're on the upstairs or the downstairs circuit. Often we'll come to a consumer unit with 3 or 4 socket circuits and they'll just say sockets, sockets, sockets on them. So it doesn't give us any information as to what might be on the circuit. So actually quite a lot of time is spent at the beginning of the day turning circuits on and off to ascertain what's on each circuit. So if possible, if you ask us to come around and do a condition report for you, it would be beneficial and it would be quicker for us if you could arrange to be out, maybe go to work that day. If you're working from home usually, if you can go into the office, or if you can go out for the day, it just means that we can get around the installation a little bit easier. The process of trying to work out what's on each circuit is shorter, and obviously there's less inconvenience if you're trying to work from home and we're turning circuits on and off and the internet might be going on and off. It's not the end of the world if you can't, but it's beneficial to us definitely if you can arrange to be out on the day that we attend. So yeah, the first piece of the puzzle when we're preparing this list of test results is to go through and work out exactly what's on each circuit. So that's what we've done here. When we're doing that, we can note down the number of points served. So in the case of the lights, that's how many lights are on that circuit, so how many down lights there are, how many pendants there are, how many wall lights there are, all that sort of stuff. So it's not done on light switches, it's done on lighting point. On socket circuits, sometimes it will just be sockets, sometimes there'll be sockets, and then a fuse spur or an FCU will be fed from that, perhaps doing some kitchen under cabinet lighting from the kitchen socket circuit, that sort of thing. So yeah, that takes up a little bit of time. As part of that, we note down the type of wiring used. More often than not, in a domestic property, the type of wiring will be what's called twin and earth, or PVC flat sheathed cable. Again, we note that down because there are lots of different types of cable, more often than not used in commercial industrial applications than domestic applications, but each of these different cable types, because of the way it's been made, will have different current carrying capacity. Some might be rated to be used outdoors, other cable isn't. And so yeah, there's lots of different factors involved, and for that reason the type of wiring is noted down. The reference method is how the cable has been installed. So has it been run through a stud wall containing insulation? Has it been run above a ceiling in insulation? Has it been clipped direct to the outside of a building? Has it been plastered in? Now it's difficult in a condition report to ascertain exactly how a cable's been installed without starting to remove the fabric of the building and have a look. So more often than not, what we will do here is, and we'll note it down in the report, we'll say we are presuming that it has been clipped direct in this case. And again, the way that the cable has been installed will dictate how much current can flow in that cable before the cable overheats. So if we suspect that an undersized cable has been run through insulation that's supplying an electric shower, a very current hungry using piece of equipment, we might recommend that that's investigated further to make sure that the cable is capable of supplying the shower. Just to give you, just to give you an idea. We note down the size of the conductors. As I've said already, the size of the conductor dictates how much current that cable can carry. So with lights, they are not very current hungry pieces of equipment, especially with LED lighting, which is prevalent these days as opposed to, say, old halogen lamps. The cable's therefore much skinnier, and it's fine being skinnier. We've got a cable here, see, instead of 1 millimetre squared for lights, this particular circuit is supplying another distribution board in the property. So that's a much thicker cable, so it's capable of carrying much more current. Yeah, so we note that down. An oven, quite a current hungry piece of equipment, so it's got a 6mm cable. Shower, electric shower, it's got a 10mm cable because they're very hungry. We then have the maximum allowed disconnection time. So we talked about automatic disconnection of supply. So in the regulations and the on-site guide, anything up to 64 amps if it's a socket circuit, and 32 amps if it's fixed current using equipment, has a maximum allowed disconnection time of 0.4 seconds. So what that means is if there's a fault, the circuit has to be designed so that the protected device will operate, i.e. kill the power, within 0.4 seconds. And actually that number there dictates what sort of readings we need thereafter to ensure that that's going to happen. We've then got the type of overcurrent protected device. So overcurrent means if a circuit is overloaded, or if there's a short circuit, if there's a fault. So when there's more current flowing than should be, what type of device is going to be protecting the wiring in that circuit. So let's just have a quick look at some of the different protected devices, because these numbers, these are BSEN numbers, which don't really mean anything to the layman. So on this example, we've got a little bit of a mix and match. This is the main switch that we talked about. So you see it's red switch. It's what's called double pole. So if you throw that switch, you will isolate both live or line and neutral. That's not a protected device, that's just a main switch. These are the protected devices, and like I said, there's a few different types. Here we have got an MCB, a miniature circuit breaker. So all of these are miniature circuit breakers, and they've got different ratings on them. So this is 6 amps, which, generalising, if there's more than 6 amps flowing, that will automatically switch off because it detects that there's an overload or there's overcurrent in the event of a fault. This one is a 32 amp MCB, which means there needs to be more current flowing for that to operate. So these are for socket circuits. This is an RCD, a residual current device. Now this RCD is protecting these circuits here. Now what an RCD does is it's a very sensitive protected device designed to protect the end user, as opposed to the MCB, which is designed to stop the wiring from overheating. Now an RCD will detect a very small amount of current flowing to earth. So if you've got metal light switches, sockets, if you've got metal casing on your oven, anything like that, if there's any current flowing to earth, which shouldn't be, not anything over 30 milliamps, which is, you know, very small amount of current, then the RCD will operate. So if there's any current flowing to earth, i.e. through the human to the floor, it'll trip very quickly. What it doesn't detect is if there's a, you know, say you're hanging a picture and you bang a nail through a cable in a wall and there's a short circuit between line and neutral. That's not the job of the RCD, that's the MCB. Now the problem with this installation, if there's any earth fault on any of these individual circuits, the RCD will trip and you'll lose all of those socket circuits, and in this case an oven as well. It's quite inconvenient in the event of a fault. Now, these tool devices here, and obviously they're different manufacturers, so that would go down as a code in a report as well, because you're not supposed to use different manufacturers within another manufacturer's board, because it might not fit the copper buzz bar properly, the cover might not fit properly, so it's just not good practice. But these are what we call RCBOs. Now these incorporate an MCB aspect and also an RCD aspect in one unit. So rather than having bulky RCD and then an MCB, you've got all that built in. So it will detect a short circuit and it will detect an earth fault as well. Here we've got probably one of the most common types of consumer unit we see, and it's a split board, an RCD split board. So you see in this instance, rather than just the one RCD, we've got two RCDs. This RCD will protect this range of circuits and this RCD will protect this range of circuits. So in the event of any earth fault here, this RCD will trip and you will lose all of these circuits, but these will still be on, and vice versa. Now this is a more modern, fully RCBO board. So there's an RCD and an MCB aspect to each circuit. Now what that means is, in the event of a fault on one circuit, you will only lose that circuit, the rest of the house will stay on. So you might lose a socket circuit or a lighting circuit, but everything else will stay energized. So these are the type of boards that when we recommend a consumer unit upgrade, we will fit these. And we'll fit these for a couple of different reasons. One, minimizes inconvenience in the event of a fault. You only lose one circuit as opposed to the whole shebang. Two, the type of RCD technology built into these Hager consumer units or RCBOs and also the company Crabtree that we like to use. They are sensitive to different types of faults. So if you've seen some of our other videos, you'll hear us talk about this. They are sensitive to AC faults, so any faults with AC current, like the element in a kettle breaking, something like that. And they're also sensitive to pulsed DC faults. So anything that's got electronics in, computer, fridge, anything that's digitally controlled that has a DC fault, the type A RCDs that are built into these RCBOs will detect that and trip. Whereas these RCDs are an older specification, a type AC. So these will only detect the first fault that I discussed, the kettle breaking. They won't detect DC faults. And so these newer units are safer, basically. And the newer type A RCBOs are safer. So that's the overcurrent protected device. There are a few different types. For domestics, this is going to be type B. And then we note down the ratings that we talked about before. So for a shower, because that's current hungry, we need a bigger breaker size to allow more current to flow. When it's lights, we can get away with a smaller breaker size. The braking capacity of these devices. This is where the fault current measurement comes into play that we talked about very briefly before. We take a measurement of the fault current at the origin. So in the event of a short circuit at the consumer unit, how many amps are going to flow? So in this particular example, it's less than 1,000 amps. It's like 920 amps. Now what that says to us, because all of these MCBs and what have you are rated at 6,000 amps, the fault current's only 1,000 amps. So if there is a fault, then these individual protected devices are going to be more than capable of clearing those faults without the actual protected device itself exploding. Let's say, for example, the fault current was 7,000 amps. Never seen that before, but it could happen. in the overcurrent protected device's breaking capacity is 6,000 amps, we're going to need to actually switch those out and replace them with protected devices that are capable of, or that have a breaking capacity of maybe 10,000 amps, because the fault current's so high.